Okay, so we're starting Unit 5 today, and Unit 5 covers a lot of physical properties of objects, so like area, volume, density. Unit 5 is also going to be a heavy dose of Inventor. We're going to do a lot more Inventor within this unit, and because we're doing so much Inventor, I don't think there's going to necessarily be a quiz when we get to the end of the unit. Today we're going to talk about geometric shapes in area, and a lot of this I'm thinking is going to be a review for you. So some of these formulas I'm going to kind of breeze through fairly quickly. All right, let's start by defining the term shape, and it describes the two-dimensional contour that characterizes an object or area in contrast to a three-dimensional solid. So examples in this case would be like a circle, ellipse, triangles, rhombus, things like that. The area then is the extent or measurement of the surface. All shapes represent enclosed two-dimensional spaces and thus have area. Right? So this is the measurement of the surface based on the shape that we are talking about. So these are the types of calculations that we're going to be doing. Let's start with the circle. Round plane whose boundary consists of points equidistant from the center. So for the center point, measuring out to any point along the boundary is the same distance, or our radius is the same at all points. The circle is the simplest and strongest of all shapes. Circles are found within geometry of countless engineered products, including buttons, tubes, wires, cups, and so on. And to understand the calculation, or to do the calculation of the area for circle, you have to understand the concept of pi. Okay. Pi is a constant ratio that exists between the circumference of the circle, or the distance around the circle, and its diameter. And the ratio states that for every unit of diameter distance, the circumference, distance around the circle, will be approximately 3.14. And so if the diameter of my circle, so the measure from one side to the other is 1 inch, then the circumference is 3.14 inches. To calculate the area of the circle, we need the radius then. So instead of using the distance that goes all the way across, we're interested in the distance from the center to that edge. And then we'll use this formula, which I think you're familiar with, to do the calculation. Okay. In this class, unlike maybe your math classes, we're not going to use pi as a variable. So you won't show your answer as 16 pi. You're going to actually do the calculation. And we'll use 3.14 as our equivalent for pi. It's close enough for the calculations that we are doing. Obviously, there's a lot more decimals, but we're not going to worry about that. So I would expect that if you were given all the variables and you're missing one variable, that you'd be able to solve for that missing variable. Right? So if I gave you area and you had pi, you could determine the radius for the circle. Let's talk about the ellipse then. It's generated by a point moving in plane, so the sum of its distance from two other points, which would be the foci, is constant. So the foci are located here. The only thing tricky about calculating the area for an ellipse is keeping in mind that the distance shown here, like from one side to the other, which is the major axis, is 2 times our A. It's similar to a circle where we use radius instead of diameter. When I do this area calculation, don't use the major axis. It's the major axis divided by 2, and same for the minor axis divided by 2. What makes this the major axis? It's the longer of the two. Right? So the longer axis for your ellipse is major, the shorter one is going to be your minor. Again, simple formula, we'll use 3.14 times A times B to calculate area for the ellipse. A polygon then is defined as any plane figure bounded by straight lines. Examples for this would include triangle, rhombus, and trapezoid. Okay, so here's our examples here. We're going to talk about the triangle first, but to talk about triangles, you have to determine the different types of angles that would make those up. So an angle is the figure formed by intersection of two arrays. Angles are differentiated by their measure. So any angle that is less than 90 degrees is considered or called acute. An angle that is exactly 90 degrees is a right angle. If it's between 90 and 180 degrees, it's going to be an obtuse. And if it's completely straight or exactly 180 degrees, it's considered a straight angle. So the triangle then is a three-sided polygon. The sum of all the interior angles always equals 180 degrees, meaning if I add up the sum of each of these is going to be 180 degrees. And I can define the type of triangle it is based on the types of angles that we have within that triangle. So if I have one interior right angle or one interior angle that's exactly 90 degrees, then that's said to be a right triangle. If all interior angles are less than 90 degrees or acute, it's an acute triangle. And if I have one interior angle that's obtuse or between 90 and 180 degrees, it's considered an obtuse triangle. The triangle is the simplest and most structurally sound of all the polygons that we would use. That's why the triangle are found in all types of structural designs, trusses. Some examples would be here. Right? So lightweight space frame roof system based on the equilateral triangle. Now the calculation for this is fairly simple, something that you've probably done before. We do want to mention the concept of inscribed and circumscribed, which you may be familiar with or not. Inscribed simply means that the triangle, or if it's, let's say, a polygon, fits within the circle, meaning that the edges of my triangle are touching the circle, the boundary of the circle, as compared to circumscribed, where the triangle is bound or around the circle, and the sides of the triangle are tangent to the surface of the circle. Here's our formula for the area of the triangle. The only mistake that people might make is they might confuse the measurement for this side A as being the same thing as the height. We're interested in the vertical distance between the base and the top for our height. Again, if you were given all the variables but one, I would expect for you to be able to find what that missing variable is. The quadrilateral is a four-sided polygon, and examples of this would include a square, rhombus, trapezoid, trapezium. Here are examples here. The formula for this is fairly simple. Area is going to be base times height. Again, make sure that our height measurement is the distance from the base to the top vertically, not this measure going up to that. It would throw the numbers off. Move on, because that's pretty simple. And then finally, let's talk about regular polygons. Polygon with all sides are equal and interior angles are equal to each other. So we have pentagons, hexagons, octagons. They're all considered regular polygons. Again, we can discuss the concept of those being inscribed in the circle. Right? So all the vertices of the polygon lie on the circumference of the circle, as compared to being circumscribed, where they're placed outside the circle so that all the sides of the polygon are tangent to the circle. For the purposes of our calculations, it doesn't really matter. But there are going to be drawings that we do in Inventor where this is important, and it's a setting that we're going to have to use. Here's some examples then of our regular multi-sided polygons like we had mentioned before. And no matter which polygon we're talking about, we're using the same formula to calculate the area. We do need to know at least the length of one of the sides and the total number of sides to do this calculation. So our formula here is area is ns squared divided by 4 times the tangent of 180 divided by n, where n represents the number of sides. So if it's, let's say, a hexagon, it's 6. And then again, s is going to be the length of that side. This one you may not be familiar with. Right? You may have done this before. This one's going to be one that we have to use a calculator to do because of the fact that there's a tangent. It would be fairly difficult to do this calculation by hand. All right, given all of those formulas we talked about, some being new and some being a refresher for you, we're going to start activity 5.1, calculating properties of shapes. And for this activity, you will use the PowerPoint we just went over and those formulas to answer the questions. Now, a lot of these require you to draw the image and add dimensions. And because of that, it may be a little challenging to do this on the Word document itself. So you may want to do this directly in your notebook. Okay? Keep in mind that every drawing may have a different unit size, right? So this first one, the grid spacing is 1 inch, meaning each of these boxes represents 1 inch when you do your calculations. So we're going to work through each of these, answering the questions. Again, notice that the spacing changes here, and we have the formulas, or they're in the PowerPoint we just did, to answer each of these questions. Keep in mind that some of them are not going to necessarily be what is the area, but given the area, let's say what's the radius or what's the length of the side. So you're solving for one missing variable. So working through each of these. This one is going to have you combine multiple calculations, right? I need to know the area of half of the circle. I have different triangles on here. Maybe a rectangle to do that. And and then one of the more challenging one here. There's 5 conclusion questions at the end of this. Those can go in the notebook as well, or you can do them on the Word document as long as you submit them together. Once we finish this activity, we're going to jump to Inventor for a couple activities. This is going to be due on Monday, so I'll give you today and tomorrow to work on it, and then we'll move on to the next activity on Monday.